Hi, in this video we are implementing the Prims Jarnik algorithm. So let's get started. I'm going to create a new package, Prims Jarnik. We are going to have a app. We are going to have a vertex. Okay. We are going to have an edge. Rename edge. Okay. And we are going to have a class algorithm. It's going to contain algorithm. Okay. So the vertex is going to be a class, of course. Vertex with the object. I'm going to define a constructor which is going to get a self and a name. So self.name is equal to name. Self that visited is equal to false. Self that predecessor is equal to none, and the self that adjacency list is equal to an empty list. Okay. Okay. The edge is going to have a class edge with the object. I'm going to define an init. It's going to get a weight as usual, start vertex and the target vertex, and self dot weight is equal to weight self dot start vertex is equal to start vertex, self dot target vertex is equal to target vertex. And we are going to use a heap, a priority queue, so we again have to override the CMP, the comparator, and less than methods. So it's other edge, return self.cmp, self.weight, other edge that weight, and def less than. It's going to have a self and in other, and we just have to return self that weight less than other that I think other that weight. Okay. Yeah, other that weight. Yeah, I think that's all. And the algorithm, we just have to use a priority queue, as we had seen in the theoretical video. Okay, I'm going to define a class algorithm with object. We are going to have a constructor in it with self, and we will have an unvisited list. It's going to contain the vertices in our graph. Self dot unvisited list is equal to unvisited list. We will have a spanning tree is equal to an empty list. Self dot is going to be an edge heap. We are going to construct a heap, and we are going to store the edges, and we are going to, that's why we have to override the comparator method here, the CMP and less than, to be able to decide what to return. So edge heap is going to be in a list, and the self that we have a full cost, it is equal to 0. Okay. We have a def construct spanning tree. It's going to get a vertex, and we just have to self.unvisited list that remove the vertex because we have visited it, so we have to remove it. And while the self.unvisited list, which means that while this list is not empty, while the unvisited list is not empty, we keep iterating through the adjacencies edges. We keep visiting every adjacent vertex. So vertex.adjacent adjacencies list. And if the edge dot target vertex is in the self dot unvisited list, so if we haven't visited it so far, it is in the unvisited list, we have to construct a heap cube. Okay, we have to import heap queue. Heap queue, we have to put it in the heap with a heap push. The heap is going to be the self.edge heap, and the item is going to be the edge. We keep deciding, we keep constructing heap because we can get the minimum. We decide the minimum according to the edge weights, so we get the minimum edge, the edge with the minimum weight, and we do it with a heap. It can do in logarithmic time complexity, so it's very, very efficient. So the min edge is equal to the heap q dot heap pop with the self dot heap edge heap, sorry, edge heap. Okay, and I just have to self that spanning tree. That's why it's a greedy implementation, because we are not going to updating the heap. We just keep inserting without updating its content. So it's a greedy algorithm, and it's worked very, very fine. Spanning tree that append min edge with min edge. Okay, print edge added to spanning tree. Okay, with min edge. Start vertex that name and the min edge that target vertex that name. Okay, so okay, we just the self that full cost plus equal to min edge dot weight. Okay, the vertex is equal to the min edge dot target vertex. We keep updating the vertex, we keep hopping to the min edge target vertex, to the next vertex. And the self that unvisited list, of course we have to update it. We just have to remove the vertex itself. Okay. So yeah, that's it. We are going to define a method. I'm not sure whether I'm going to use it or not. Def get spanning tree, and we just have to return self that spanning tree. Okay, so in the app I have constructed it. It took a lot of time to do it, so okay, I'm going to from Prims Jarnik dot edge import edge from Prims Jarnik dot vertex import vertex from Prims Jarnik that algorithm import algorithm. Okay, I have to import it because it's not the thing I wanted to import. Open project with this app. I have tested it. Oh no, maybe it is. Yeah, maybe this is. Okay. Anyways. So it was good. We have an unvisited list, and we just have to create an algorithm with algorithm and algorithm dot construct spanning tree with for example, we have to specify a starting vertex. It's going to be this, or oh yeah, it's the constructor. Okay, we have an unvisited list here. Okay, so let's run it, and of course we can test it. That the spanning tree, it has 4 vertices, and because it's very cheap, we can construct it with the help of 1, 4, 1, 3, 1, 2. If it's going to be very big, 9 for example, then it has another solution, 1, 2, 1, 3, 3, 4. Yeah, so it's working fine. It is the greedy implementation of Prims Jarnik, and it's very efficient. So most of the time in the practice we use Prims Jarnik algorithm. Thanks for watching.